Okay. All right. So 3.1, I think is probably the most straightforward of the sections. And the big idea is that a quadratic function can be written in this form, and they call this standard form, or you'll see it sometimes written as vertex form. And what this is this tells us what the parabola looks like, right? A quadratic function is a parabola. This parabola is going to be centered, or the vertex is going to be at HK. And then the A, this determines whether it opens up or down. And it also lets us know if we have any stretch, let's just say, any vertical stretch or compression. So for example, if you see f of x equals negative 2x minus 3 squared plus 1, right? I look at that, I know that's a quadratic because of the x squared that I'm going to get. It's written in the standard form or vertex form. So I know the vertex is at 3, 1, right? It's the opposite of that value. Right? That's the vertex, which is the most important point. And then after that, I look at this. The negative tells me that it's going to open down. And the 2 tells me it's been stretched by a factor of 2. So a normal parabola, an unstretched parabola, I would go over 1 and down 1 to get my next point, right? It's not a line, so I can't just continue going over 1 and down 1. But the first point on either side is the over 1 and down 1. But because it's 2, I go over 1 and I go down 2. Right? And that creates a sketch of that vertically stretched, right, parabola. And we can also, of course, take the parabola and go back to there. Okay, so there's a little bit more in there, but that's really the key point of quadratics, is working with that equation and different forms of that equation. There are some questions where you have to kind of figure out where it is in standard form. Remember, I guess it's worth mentioning, if you have an equation, a quadratic that's written like this, the vertex is at negative b over 2a, and then the easiest thing is just to put that, whatever number you get there, to put it into the function to find the y value. So that will tell you the vertex, which you can use to find that, and the a here is going to be the same as the a here. So if you have a function in this form, you can complete the square to turn it into this, but it's algebraically sometimes a little challenging. I think most of the time it's easier to just figure out what the vertex is and then use that to plug it into the original form. Okay. There's a couple application problems of sorts, but they're, again, mostly just relying on this idea that we know what the parabola looks like, and the vertex is where that parabola has a maximum or a minimum value. Okay. I think the most challenging sections, the most challenging sections for most students are this 3.2 and probably 3.4, which is talking about zeros of polynomials. So I kind of hinted at this last week, that we want to be able to kind of understand what some of these higher degree polynomials look like. And so take a look at one here. Let's try x cubed plus 6x squared plus 9x. You can work with that. So this is a degree 3 polynomial. The fundamental rule of algebra says that the polynomial will have 3 zeros. So if it's degree 3, it has 3 zeros. If it's degree 6, it has 6 zeros. If it's degree 100, it has 100 zeros. Now some of those zeros might be the same, so they're not always distinct zeros, but there will be 3 of them. Each zero corresponds to a factor, x minus a. Okay. So if a is a 0, x minus a is a factor of the polynomial, right? And a 0 means f of a equals 0. X equal a is then also an x-intercept. So all 3 of these things are equivalent to each other. So a 0 of a function means we have a factor, a linear factor of the function, x minus a. And it also tells us that we have an x-intercept because, of course, f of a equals 0. So that's going to give us an x-intercept. So when we're looking at these polynomials, we are very interested in what the zeros are, right? That's really, in some ways, the primary, well, one of 2 primary things that we care about when we're looking at polynomials are the zeros or the x-intercepts. The other thing that we are interested in is what's called the end behavior. And what the end behavior means is that actually as x gets really large, this function is no longer going to look like these parts don't matter. And the function will begin to resemble whatever that leading coefficient is, x cubed. And so we want to know that an x cubed function looks like this. And actually that's true if you have x cubed or x to the 5th or x to the 7th. Any odd power of x will resemble this end behavior. If on the other hand I have x squared or x to the 4th or x to the 6th, that's going to resemble this on the ends. And what I mean by that is eventually, if it's an x cubed, eventually the function is going to come down on this end and up on this end. It may do lots of other things in between, I don't know, ups and downs and whatnot, but on the ends, it's going to head in these directions, right? Same here. And then of course, if I put a negative in front, that flips everything, right? That's a full flip. So a negative x cubed and a negative x to the 5th would just flip the direction here, right? Same here. If I have a negative, it's going to flip it upside down. So when I look at this polynomial, I know that it's going to resemble this on the ends. Based on this leading coefficient. And the second question is, what about the zeros? What's happening at the x-intercepts? And what's happening to the polynomial? It turns out that it can have at most n minus 1 turning points. where n is the degree. So for us, that's 3 minus 1, which equals 2. So it can't go, right? That's way too many turning points. That's not possible with a degree 3 polynomial. It can only have 2 turning points, up and down. It might not have that many, but it can't have any more than that. So the larger the polynomial, the degree, the more possible turning points there are. This is all our theory, so we get a sense of what the polynomial is. Not a perfect graph, but we know we can sort of limit it and put it in kind of a box. I know roughly what's going on here. So to find the zeros, there are a number of different strategies. You'll learn some of the strategies as you work through 3.2 and a couple more as you work through 3.4. But the basic easiest strategy is if you have a polynomial like this, you can start to factor it. And factoring is important to this section. Factoring is going to help us in this case because we're able to, it's 3 factors. This one is x minus 0. And so this tells me the zeros, 0, minus 3, and minus 3, right? I have 3 zeros because it's a degree 3 polynomial. It happens that one of those zeros is repeated. And when it's repeated like that, we say that has 2. Okay. Technical issues here.